All right. So yeah, this homework, I want to go through the homework today. It's due on Wednesday, but the next homework's due on Monday. It's kind of like, and it's this software thing, it's this lamps thing, and the guy's going to go through it on Friday on Zoom. So I'll be here if you don't have a laptop, and at least one of the people doesn't have a computer at all because they do all the homework in writing. So if that's the case, then you can just team up with someone or figure out some way to, huh? Yeah, but you can't, I think you can't this requires downloading that software. You have to download the stuff from GitHub or something and then set it up and then run it. So if you use, yeah,
So you're saying that this week's homework 12 is due Wednesday, and then homework 13 will be lamps due next Monday?
yes. Yeah, because I think the lamps thing is going to be like you're going to have to sit down. It's not like a learning thing exactly. It's more like a discovery thing. And it should be that everyone can do it, but it's going to be just a matter of putting in a little bit of time. So you just have to find between now and you could do it before it's talked about even. It's all right. So there's a web page. Let me just go to that. So I realized I got to like fix my web page better somehow, but so it's this thing, and then it's just a web page. If you go to that web page, it's step by step. That's what's nice about this. This guy's in Edinburgh. And in the end of this doing this thing, if you do this super quilt, so the Polymer thing is like they can he has one particle, then he does a Polymer chain, and then he does with stickers. This is what we've seen that before. So the idea is like they're called vitrimers now, where you can make a network and it can unnetwork. So you can have like a recyclable tire is the idea. So if you could cross-link it, then it could flow again, and then you could somehow make another tire with it. Or you can have self-healing rubbers and things. Self-healing plastics is partly vitrimers too. Anyway, so but in biology, the idea of that came from biology where you have these kind of networks that can form and unform, like if you change the pH or change the temperature, these kind of hydrogen bonds and things can break, or ionic linkages, or you can see like you can salt out a shampoo and it goes from being a gel to being just like liquid, right? So, or water even. Anyway, so this goes step by step through it, like even like how you download the software and everything. It's just like go through this. And then Hugo will go through the entire thing on Friday. And you can, if you want, you can do it at home on lamps, so you can come in and do it. I'll be here. So and then mostly he's agreed to take questions and stuff about it to help you with it. So he's done that in the past, but now he's a postdoc in University of Tennessee. So it's kind of odd that he's doing it as a favor, but I think he likes working with people. Like he enjoys doing it. So um and I think he's not like that busy for some reason. I'm not sure why, but he should be really busy. But anyway, so there's that business. So that's for Monday. Then for this week, we got this thing. So let me just get these all open. I added a couple things here. I'm not sure this is just something related to it. And then so this thing, and then this Jorge paper. So Jorge is a guy, he worked at, so this is a really long paper. It's like huge length for macromolecules, 1/5 of an issue of macromolecules, which is a lot. Like it's insane. It took me like 3 or 3.5 days to read it, like it's thick with a lot of equations and scaling theory. So it's all the stuff we've been talking about, but you have to go through each equation to figure out what's going on. So anyway, the homework is just pretty fluffy. It's like just kind of generally what's going on in it. So I'm not sure at what level I want you to read this paper, because it's a little bit too much. Um, it's a pretty good paper, I guess. So this guy, I guess this K, I guess K in Chinese means food. right? So, or it can mean a dish. So, say like Chongo K means Chinese food. And I probably don't get the intonation right, I'm finding out. Because the program I'm using to learn Chinese keeps rejecting everything I say. Been on the same lesson for like 3 weeks. It's like just I can get the first part and then it gets to the part and it's just like I'm saying exactly what they're saying, But it says, no, you aren't. So I've gone to just learning how to pronounce things. But anyway, this means food or dish. Mago K would be like American food. Jingo K would be English food. And Korean food is Raibo K would be Japanese food. I don't forget Korean, but anyway. So he means food somehow. But anyway, so he's a young guy at University of Virginia, which isn't really known for polymer. I'm not sure what department he's in. Let's see, I think chemical engineering, but let's see, he's done. Macro puts it like this. Some materials, there. But then, so he's got the career award from NSF, this career award DMR. That's like a 5-year award for when you're starting out. So it's kind of hard to get. And then he's got an NIH grant, and then he's got this funding from this diabetes foundation fund. So it tells you like this interest in this stuff from biomedical. So Jorge work is a polymer physicist who I guess he was for a while, he was like, did something at NIST. Like, but he's at NIH. And then he published this. This only has 2 citations. It was kind of weird because he's like a pretty famous guy. And I think this guy's also pretty famous. This is a PRL paper. It's not referenced. Let's see. In our paper, he talks about aggrecan, which is a protein, right? And this protein, so it doesn't look like much. It doesn't look anything like a bottle brush polymer, right? But it combines with uh, like carbohydrates. A carbohydrate molecule couples with it, and then those two make a main chain, like a backbone, and then other proteins, specific proteins, come and make the side chains. So the whole thing is 0.4 millimeters, 0.4 micron long. So it's pretty big. I mean, it's maybe 1/100th of a human hair diameter, but it's big for a molecule. And then the side chains are huge, compared to the ones that K's using. But this ends up being the thing that is the majority of your joints, like like your bone joints. And this is the thing, if this thing falls apart, so if a protease, like we went to the seminar, the guy was talking about proteases. You make a protein, it can fold into the nice state, but there's something wrong with it. You got to get rid of it because it's like a gun floating around with little kids. So you want to get rid of the gun before it starts killing things. So there's a protease is how you get rid of the mistake proteins that are made, right? So it's important to make things that are functional. It's also important to get rid of things that are dysfunctional. Equally as important, I guess, in medicine, right? Anyway, so this this thing ends up being like if this thing gets to be wrong, then you get arthritis, basically. This is like the main thing in joints. So you need to get rid of this thing when it misfunctions. Anyway, so if that's why NIH is interested in it, is for the bone stuff, and apparently it has something to do with diabetes too. But anyway, so it is a bottle brush thing, and it generates cash for research. If you can tie it in, everyone gets arthritis. I'd say like probably 90% of the people, when you get over 60, have arthritis of some form, Maybe certain ethnic groups don't, but white people do, and they're the important one, for some reason. Right? So somehow these things get to be like money generators for research. So even though Jorge is a polymer physicist, so he's milking the cow, and the milk keeps coming, so he keeps doing this. It's interesting too, but basically it's a cash for research type thing. So he does neutron scattering. So this might have been a better paper to look at, but it isn't this year. It's like a couple of years ago. So he's looking at those kind of materials that are bottle brush polymers, and he's doing like neutron scattering So he gets the size of the bottle brush and then the internal structure at the high Q, or you're looking at the internal structure, and he's got some models for what's going on. So I put that up there too. I put a link to this thing in case you want to see how these things fit together in a sense. So that's how K is sitting here with like, this is a 5-year, like $1 million, $1.5 million grant. And then he's got this NIH thing, which is probably like $10 million. Like, all right, so NIH has literally 100 times the money that NSF has. So it's almost less prestigious to get an NIH grant than an NSF because it's harder to get an NSF. You know, so anyway, he's got both of those, and then he had startup money from this thing, internal grant system at Virginia, which isn't really a place that's known for soft matter. VPI is the Virginia Polytech, which isn't far from this place. This is Jefferson School, like Jefferson founded University of Virginia, Thomas Jefferson, like in the 1700s, whenever that was, right? So it's like, this is kind of a prestigious school, and Virginia Tech is more like a engineering school. Probably Virginia Tech probably has more money than University of Virginia, so whatever. Anyway, he's there. And then, so first thing he does in this is he goes through, so it's interesting. All right, so people kind of came up with the idea, chemists, came up with the idea of bottle brush. So you can have a polymer and you can make a star polymer. That's easy to do. So you put in a multifunctional site, like you can use TIAS or something, so this kind of topological polymers. So bottle brush grew out of the topological polymer family things. That's pretty good. So you have, if you have these silicon, so this is easy to do. Like you can do this in your kitchen, you can buy this stuff, and then you can buy in-linked. So this with methyl groups on it, and just hydroxyl in groups, so an H here, another OH here. That's siloxane. You can buy a bottle of that, you can buy a bottle of this, and it'll just sit around, nothing happens. If you just make that acidic, these groups will, so you can polymerize that by making acidic or base, anything away from the isoelectric point. So it can form by base or acid. So isoelectrics around like pH 6. Right, and then that'll make a chain of bathtub caulk with methyl groups on the side. That's silicone, like silicone elastomer. Right? Breast implants, a lot of medical tube things. And if you just throw in some of this, it's got 4 of those kind of OH groups on the end. That'll make ethanol or booze as a byproduct, and then it just will make a tetrafunctional thing, right? So you make a star polymer that way. If you have 2 of these hooked together, then you get 6 arms, and if you have 3 of them, you can imagine you can make any number of star arms that you want. And then if you put this stuff in, then you can make dendrimers from it. So you can make these topological things, right? That's one thing you can do. If you want, you can start thinking about different topologies. So one of them is like a comb polymer. Like you're going to have so you can imagine any kind. You can make an H. They have H polymers. Anything you can think of. A T polymer, I guess, is just a single one of those TIASes. If you kill off one of these and make it a methyl group, you make it a T polymer. You can just start playing around with this. And it's not just this. The reason I mention this is that you can do this literally in your kitchen. Like this is really easy chemistry to do, right? But the other chemistries might be a little bit more elaborate. But basically, you can make all these topological polymers. So that's called a comb, right? It's going on both sides of it. And then he's got a loose comb and then a dense comb. So he's defined, not him, but the Russian guy. What's his name? Let me go back. The Russian guy. That's K also. This guy, Rubenstein, right? So he's co-author of that Polymer Physics book that with Colby that's on the webpage. So he's kind of a famous Polymer Physics guy. Let's see. Colby is pretty easy to understand, kind of, but this is a little bit more elaborate. That's not what I wanted. I wanted to do a search in here. Doesn't let me do it. Anyway, down at the bottom, Colby's book is in here, which is something you should have probably looked at. Rubenstein, Colby, right? This thing. So anyway, so where's Colby's thing? Here. So he's talking about bottle brush polymer. So once you get so this paper is like the seminal paper. This has like 1,000 citations. So it's like pretty heavy. Like a lot of people look at this paper. It's the theory of bottle brush. I guess it's fairly recent, like 20, you can't read it, like 16, right? So that's kind of an important paper. It's in the Science Advances. I guess it's a kind of a newer journal. I don't know. I think it's somehow anyway. So the first part of this paper, so that's also like a 20-page paper, right? So the nice thing about this, so I thought about just the homework, just say like conventional bottle brush, just go through the first part of this, which is a 2-page summary of everything that Rubenstein did in that other paper, which is nice. That's palatable, you know. It's not like cramming food down your throat, you know. It's like, oh, I can't eat anymore, you know. So it's like 20 pages is too much for a week. I mean, it's just like insane, right? So anyway, yeah, we did it. So he's going through the 4 phases, what Rubenstein's 4 phases. So he's going to try to mimic this for different kind of systems. So in Rubenstein's thing, the main chain and the side chains are the same stuff, like the PDMS. Like you just have a bath of PDMS and you just make the thing up, you know. So it's all the same thing. So that there's, he says the chi parameter, so the interaction energies between the two is 0. That's called an athermal system. It means there's no enthalpy of interaction, but there's still entropy issues. So the whole system's governed by entropy, right? So it's not a Gaussian system, it's an enthalpic system, athermal, no enthalpy driving it. So there's a distinction between ideal, like a Gaussian state where the thing can pass through itself, and then there's an issue of like, do they have enthalpic interactions? The way to get the thing that passes through itself is not athermal, it's to have an enthalpy that exactly balances entropy, right? So it's important to make that distinction. So you think like, oh, if I just get rid of enthalpic interactions, I'll have an ideal gas, you know, and it's not true with polymers. So basically you have to actually balance the enthalpy and entropy to get an ideal gas, an ideal chain, right? So anyway, so this change, you get rid of that, so it's all governed by entropy of the chains, right? So he has these regions. So would be a comb polymer, like a loose comb polymer would be here. That's all, everything is Gaussian. So it's in a melt, so everything's Gaussian. So it means you have Gaussian side chains and a Gaussian main chain. So you can say the end-to-end distance, it's all going to be square root because it's NL squared. R squared is NL squared, so square root of N. This should give you Gaussian stuff when you see 1/2 in here. Everything's Gaussian when it's just loose. Then you start to bring the more of these side chains onto the thing, and they're long side chains, so they're polymer chain side chains. So what happens? So if you look at one of these, these are there's a segmental chain. So NG is the distance between a side chain along this. So if you have high NG, it means you have few side chains, and low NG means you have a lot of side chains. And when you go to 1, every monomer in the chain has a side chain, right? So the monomer is a chemical unit that you can attach a side chain to. So it's got physical relevance in this case. And then there's another kind of unit, which is the Kuhn length, which is going to be composed of more than one monomer. So it's possible to have more than one side chain per Kuhn length. So you can have a rigid steps with many branches off it, right? So things get a little interesting here. I mean, it's kind of mixing up chemistry. Usually you think the chemical unit is a meaningless unit, but here it's got meaning because it's a limit to how many side chains you could have on this brush polymer at that point, right? So as you go down here, you have regime 1 where the things are independent, the side chains are completely independent. And then regime 2, which he has pretty long here, the side chains can interpenetrate, but they aren't, there's no force between them. So it's kind of like, it's before they would deform each other, so they can kind of interpenetrate with each other, right? So they aren't deforming, but they're interpenetrating. And then you get to this, so if you have side chains of molecular weight in side chain, then when your spacing of the side chains reaches in side chain, you go from regime 1 where they don't interpenetrate to regime 2 where they interpenetrate, but there's no difference in the behavior. What's plotted here is let's see. What's plotted here is the let's see, can't read it even there. The backbone, all right, so the backbone, if it's Gaussian, and the backbone, so the total length of the chain, one end to the other, so that's 1 when you're in regime 1 or regime 2. So regime 1 and 2 are kind of similar. All right, if it was in a good solvent, then regime 2 would be the concentration blob. So it'd go from expanded coil to a theta coil. And it would go through the concentration blob thing where it would eat it from outside to in. So on large scale, it would be Gaussian, small scale, it would be expanded coil. As you made it more and more concentrated, making NB smaller, NG smaller, it would penetrate more and more, so you'd get this transition. So you can see this whole thing has to do with blobs. It's a total blob system, right? So anyway, so and you can imagine, like, so you're going to get, like I did in class a little bit, these calculations, well, they become a little bit more complicated because you're looking at the side chain calculation and the main chain calculation, and they influence each other. And then you have this other thing, which is NG, the spacing between the side chains. So you have, and then you have the Kuhn length also. So there's a bunch of size parameters in this, some of which are blobs and some of which aren't blobs, right? So the question here is, though, just deal with tensile blobs, right? And say, like, where, so the question on the homework is like, where do tensile blobs come into this? Because if you see, these chains end up being totally stretched straight, right? So that's dealt with as if it's a tensile blob, like they have a force on it, and the main chain ends up being totally straight at some point, and that's a tensile blob too. So both the side chains and the main chains go through this transition of tensile blob if it's all Gaussian in a melt. I mean, if it's in a solvent, then you get also concentration blobs and potentially thermal blobs, which would make it even more problematic. So at some point you just say, like, let's just talk about Gaussian, yeah, because it's already bad enough, right? So anyway, so that said, I thought I wouldn't have enough stuff to talk about with this, but even just this one part is probably a lot. So that's why if you go through the math, it's going to take you 3 or 4 days. I mean, not full time, but basically looking at it. So basically total of like 5 hours, but you can't stomach it for more than an hour, because it's getting too much stuff, It looks like a pretty interesting area to work in, though. I would think, I've thought of, like, after reading this stuff and thinking, like, yeah, we could do something with that, There's some area you could contribute to this. If you start thinking about, if you're a chemist, especially, and you start thinking about, say you can make the main chain, it doesn't have to be all, so what K does is he goes in and he makes the main chain incompatible with the side chain, so he gets a micro phase separation, like a block copolymer within the chain, or like, so that's interesting. But you could also make this really the main chain really a block copolymer, like A, B, A domains, and then mess around with that. Like, there's a lot you can mess around with here, actually. So the idea is when you get to this joint thing, the point of the joint thing is that with the same force, it can extend. So normally if you pull on the string or on the cable and you pull on it, it gets harder and harder to pull it, right? So there's an extension and tension relationship, right, between normal materials, but that's not true of your joints. And I think the magic of your joints somehow is that you get this behavior that he shows it at the end here. The last plot is the point of this paper. This thing. So this is extension. So we normally have strain, which is the length over the original length, and the beginning of strain is 1. Like the length is the same as a beginning length, right? So lambda is a thing that goes to 0. It's like how much did you extend it, not how much. So it's 1 plus strain would give you lambda. So if you talk about molecules, you'll usually deal with lambda. If you talk about a brick, you're talking about strain or whatever. So macroscopic is strain, microscopic is usually lambda, like all the rubber elasticity theories in terms of lambda. So 1 plus a strain. So anyway, usually the more you strain it, the modulus, so the modulus decreases and you get more strain. So if you plot the modulus of a material versus the maximum strain you can do, and it's like that, right? So you can't have a high modulus material that strains a lot. It's counterintuitive, right, to have that kind of material. But the material he's made, which is this phase separated, where the side chains and the main chain are incompatible, has the opposite behavior, and that's the same behavior that you get in your joints. So this is like of interest to people at NIH because they want to make artificial joints, or they want to understand why people get arthritis. When you get arthritis, those proteins get degraded, apparently. I mean, I don't know anything about it, but that's what it says, like whatever, Wikipedia or wherever you look, So basically the issue here is, how do you maintain this kind of behavior? First, how do you get that kind of behavior from a bottle brush-like molecule? And then how do you maintain it if you don't want to get arthritis and you become crippled, So it's important. I mean, of course, Trump has cut all the funding for all this stuff, So we will never know, not until something else in an alternate universe happens, So there's promise for time travel, but all right. So anyway, that said, that's his kind of his motivation. I think the motivation was first like, this looks kind of interesting. Then like, second motivation, how am I get money to do this? Third motivation is like, we can cure arthritis. So it isn't exactly like he woke up one day and said, I'm going to cure arthritis. I'm going to use bottle brush polymers to do it. So it's kind of a sequence of events, and it involves capitalism in the middle. Like, how do you get money? It isn't exactly, it's just like, how do you survive in a research environment? And you have to pitch it to the guys who have 100 times more money than NSF. And then eventually, who else? Like, somehow you're going to sell it to Musk, maybe you can use it to get to Mars or whatever, So anyway, there's different ways to spin things, but there is a legitimate case that this could cure a disease that troubles a lot of people when they get old, and some young people too, as juvenile arthritis too. But so anyway, so you got like, so there's nothing happening to the size of the backbone in this region because they can overlap, like they're allowed to overlap up to a point where the pervaded volume, so he talks about the pervaded volume. So the chain itself has a volume, the side chain, and there's a volume that's allowed in the geometry of a rod in the space going out from a rod, which are kind of cones for each of the molecules. The molecules are all mixed, but there's kind of a cone that it could occupy, right? And when you reach the side chain length in terms of the backbone spacing, then you go from regime 1 to regime 2. That's where the things start to interpenetrate. And then you reach to that point where the chain volume is larger than the pervaded volume, so it can't just mix anymore. It doesn't have enough space. So then you start putting tension on it, like a tensile blob. So then the question is, which thing do you put tension on? Like, the interesting transition is that you have the same stuff. You have the backbone, then you have these kind of side chains, right? And then you have this point, right? So you can kind of take the side chain out, and it's got that point. So there's a tension on that point, a three-way tension on that point, right? But the side chain only has tension like in one direction, and the main chain has tension in two directions, the same tension. So that the force that you're putting on it is 2 times for the main chain as it is for the side chain. That means once they reach the pervaded volume, which is again like a cylinder somehow going out from this, that force is gonna be concentrated on the main chain, not the side chains. The side chains are not perturbed at all, right? And the main chain is what's perturbed, and it goes into a tensile blob operation. Those are the blobs. There's the blob size. Right. So once you go from this some kind of magic number of the size between the branches, then all of a sudden you're going into this regime where you're pulling on the main chain and the side chains is still happy because they reach the point where they reach the pervaded volume, and it accommodates a closer spacing by stretching out the backbone. So the backbone is being a tensile blob, and it's getting smaller and smaller blobs up until a point where it's fully straight. And the side chains are just happily flopping around. They don't even notice, right? So, because they don't know. So basically, once the backbone is fully straightened out, you reach the second magic number, which is NG double star. Creative names, but basically NG star, NG double star is a transition in regime 3. Regime 2, nothing happens except that the chains are interpenetrating, so they're entangled. Side chains are entangled. So dynamically, something happens in regime 2. Like the motion of the thing changes. It goes from a liquid to like a network and some time scale, right? So if you did QENS on this thing, you would see the dynamics change from regime 1 to regime 2. So there's a lot of experiments. So you can see you're writing proposals in your mind, like how would you study this? And like you can see like there's a lot of things you could do to just study this. Like deuterate the side chains, so you only see the side chains, paint them red, then see if you can see the dynamic transition between 1 and 2. That would be like a NSF proposal. If you could say how that could cure arthritis, that'd be 100 times more money from NIH. If you could say how to get to Mars, then you just write your check, whatever you want, you know. So then you're in Musk land. But so anyway, there's this region, and then in that region, then the coil straightens out by this 1/2 loft, or what, and he gets that by a scaling by a tensile blob. And if you want to see, so you can read. So all these scaling regimes, he derives all of them in here. But this was derived by the Russian guy, Rubinstein, or Rubinstein, depending on if you're German or American, I guess. But so anyway, so anyway, that's that. And then, but in here, see the side chain, this is the side chain, it's just exactly the same as if nothing happened until it reaches the backbone is totally stretched out. And then the side chain does the same dance as the main chain. And then in that region, the main chain is kind of, I forget what the 1/4 is from, but basically this thing stops stretching anymore. It's totally straightened out. And for some reason it goes 1/4. I think it's because the total size of this R, whatever total size, is affected also by the side chain size. I think that's what it is. So basically the side chains go into this tensile blob regime here. So this 1/2 is the tensile blob regime for the backbone and then the side chain. So it's a nice, neat little story. Evidence for it, I'm not sure. Well, some evidence is probably, if you look in this paper by Jorge, in this Jorge's PRL thing, where he's talking about basically the arthritis thing, right? So anyway, so that's nice. And that's just a background. That's just this, all he does there is like summarize this paper by Rubinstein, wherever it is, this thing. So he's just summarizing this, but you can see this is a pretty long paper. So he does it in like 1.5 pages. That's nice. That's pretty neat. So the thing he's interested in isn't that, he's interested in, if I make this backbone out of something that's incompatible with the side chains, then what happens? So incompatible. So chi bigger than 0.1. Usually chi is 0.001 or 0.02 or something like that. And if chi is positive, it's admissible. If it's negative, it's admissible, right? So more or less. Chi, I mean, you have to factor in the entropic part. So it's the chi part and the entropic part has to equal 0. Then you have Gaussian. So chi can be a little bit negative, and it's still immiscible. And then when chi gets really negative, overcomes the entropic part, then it becomes miscible. Right, so this idea, like you have to balance out the entropy and the enthalpy to get the point where it's zero. So chi zero means it's still immiscible, even though so chi zero here. So anyway, they haven't factored in the entropy part, but anyway, so he goes to that. So he's just got another graph like that for his immiscible one. So it's completely immiscible. Chi's 0.1. That's a big number for chi. You know, chi's a ratio of energy to KT and 0.1 per monomer. If you multiply chi by n to get the total, and n's 10,000. So it's 10,000 times 0.1 is 1,000. Ratio of the energy of the thing to the KT, which is where you're living, right? So it's 1,000 times immiscible. If it was KT, it would be kind of miscible, I guess, you know, but it's 1,000 times immiscible. So it's totally immiscible. Means you can have a really sharp interface. Like it's going to just be boom, cut one phase, the other. So this is like he makes the analogy to block copolymers where you get micro phase separation. So it's totally immiscible with side chains, but it's covered in side chains. So it's like it can't make a bulk phase of the backbone. It can only make a bulk phase with hairs on it that are miscible with the other hairs and other polymers. Right. So it's not going to make like oil and water. It's going to make like a block copolymer where you have spheres, lamellae, rods, or double diamond or some weird thing. Right. So anyway, so he's going to go through the same regime. He's going to have like comb, like loose comb, dense comb, and then loose brush. So loose brush is where where there's the pervaded volume doesn't reach enough, so you have to start stretching it. And he's going to go to like dense brush, but he ends up with 3 instead of 4 on this thing. So he has like, so what happens? So what happens is totally different. So when you're in regime 1, you literally get like a micro phase separated block copolymer. There's many chains, and then because there's enough space that the branches can go to the surface of spheres. So sphere has the lowest surface area possible. So so the chi interaction is going to be only at the interface, and it's a bad interaction. So I have the least interaction that you can. You get that with the thing with the lowest surface area. So it's a geometric issue. You just want to find the object with the lowest surface area, which is a sphere. All right. So what's the radius of the sphere? That's going to be if you have the side chains at the surface and the chains, between the side chains, this NB is like stretched out, and then you have the side chains, and that's the largest sphere that you can make. Ideally, you'd want to have oil and water, so the large sphere would be like meters in size or kilometers in size, if you could do it. But because the branches have to be at the surface, because they're so immiscible, they have to be at the surface, and you have a sharp interface, then it has to be that's going to be the size of the sphere. So he's got what's he got plotted here? This is what? A, B, C, D. Scaling regimes, dependence of equilibrium sizes of the side chain, RGSC, that's here, and the radius of the collapsed backbone, RCE. So this is the backbone. Well, he doesn't exactly have an axis for this, but this is the backbone radius, which is going to be this sphere. So he's gonna do that as much as he can, and then at some point, this thing becomes, all right, so this Q is a number of chains. The number of chains, so it's more than one chain at this point. When it's loosely grafted, so you have a large NG between the graft points, the branch points, side chain points. Then this is a big distance, and you can fit more than one chain into this sphere. And then as you go down, you reach a point where you can't fit one chain. All right. So the logic of the Rubinstein stuff is clear cut. It's 100%. Like that must be true. Like you follow it through, and it's like yes, 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 yes. Okay, done. Now that has to be the way it is. The logic of this thing is a little bit fluffier. So K's thing doesn't seem to me to be exactly as clear cut as the Rubinstein stuff. So you have to kind of keep that in mind. K's a new guy, and Rubinstein's a guy who's been around for a long time. So basically maybe Rubinstein knows more. It's hard to tell. But anyway, it's still interesting. So he goes down and he says, so this might be his imagination, is what I'm saying, that it's going to go from Q being many to Q being one at some point. So when you get to NGC, there's just one chain inside that thing. And then at that point, the chains can be, so between the side chains, they can be crumpled up Gaussian, but basically you can only fit one chain anymore in it when this gets to be too close spacing of the side chains. So there's going to be a transition point, this NGC, where you have to make this into a rod. At that point, it has to be a rod of spheres instead of spheres, individual spheres, with chains that can wander in and out of it. So this can have Q as a big number. Q's capital Q's how many chains are in one of these things, and Q goes to 1 here. There's only can fit 1 because NG gets too small. And at that point, this thing turns into a cylinder. So this is called his thick cylinder, or I think it's called the thick cylinder regime. Let's see. I notes on this. I have like a pile of notes on this. I'm trying to figure out someplace here. Yeah. This is the notes on this one paper. Then after reading it, I got through and I'm like, I can't ask you guys anything about this. It's like too much. And then I just said, like, where is it that the tensile blobs show up in it? The whole thing. So there's a thick cylinder, he calls it. So this is regime 1. Regime 2, regime 1 is a sphere regime. Regime 2 is a thick cylinder. And then he says, well, the Kuhn length is important here because you can get below so you can have the distance between branches is smaller than the Kuhn length. Then what happens? And this is where he gets into what he calls a foldable brush, which is his magic material, the joint material. So how is it that you can have extension? You can have a high modulus and still have high extension. Like nothing exists that way. There's no material that exists that way except your joints and this stuff, right? So this is like a unique feature. So it has to have some kind of unique and interesting description of it. So he comes up with a scheme for it that once you get below the Kuhn length, then you have this fixed. So this is NGK, Kuhn length. And this NGC is where you can only fit one chain into this phase separated domains. Again, this is a lot fluffier than the others. You have to be a lot more critical about this. Like this is just blowing out of his ears, right? He's just kind of saying what could possibly be going on and how could I get this higher modulus and higher extension at the same time? And this is the scheme he came up with. So it may or may not be true. I think the Rubinstein thing seems pretty straightforward, right? Except some of the math might be messed up, but basically this thing you have to start questioning, like, this is the bulk of the paper, right? So anyway, nonetheless, he gets to this point where there's a second transition. And at that point, you have to take the Kuhn lengths so that it can't bend the Kuhn length. It's stuck as a rod, but he's got more than one branch coming off the Kuhn length. So this is his thin cylinder. So this is a thick cylinder. Is that what he called it? Yeah, thick cylinder regime 2. This is a thin cylinder regime.
In transition between region 1 and 2, I mean, at NGC,
Yeah.
how do they recognize the NGC? Because it's similar in these two regions.
Well, I mean, you can see spheres and you can see cylinders. Like you see, morphologically, you can distinguish it. Yeah, from the plot. So the size is the same, but this is a sphere and that's a cylinder. So you can see it. You can do a scattering. This is a rod. So that's got a regime of 1, and this would be if you looked at the high Q, it would be a power law of 4. So if you did scattering from this, I mean, it doesn't look like from the plot like the size of it, you can tell, but I probably should have asked you to do the scattering from this. Basically if you do log I, log Q, so one of them is going to be -1, right? So So, and then it's gonna end, like that'll be like the rod length, that's his R whatever, backbone. Right, and it's gonna be one. This is a rod, and then it's gonna have a diameter, it's gonna go to 4 as a surface scattering machine. So 4 rods long, and the slope of that is the surface to volume ratio. Basically, that's the diameter, that's his R. I don't know, it's R little r or something, right? So that's one of them. The other one is gonna be like that. It's just a sphere. And in fact, the spheres are monodispersed, so they'll have oscillations here that are. They'll have oscillations because it's a single size object. So anyway, there's oscillations in it for a single size. You get oscillations for the cylinder too. But basically, between those two, there's a huge difference. That's going to be on the order of how many spheres in a cylinder per cylinder. Like in other words, you're going to get maybe hundreds, right? So that factor is going to be 2 orders difference. So you can easily in scattering see it. If you do TEM on it and somehow contrast and see it, like there's a difference between dots and a rod, right? I mean, and you could probably do a hydrodynamic radius like BLS. You could see the difference between rods and. Right, so there's probably many ways to see that the size scale here is a rod diameter size scale, which doesn't change. So you go from a sphere to a rod, they have the same passageway through them, right? But basically, the structure has changed there. That's easy, should be easy to distinguish. And then he gets down here, and this is where he has this kind of transition from a thick rod to a thin rod. And the thin rod kind of has a fixed diameter. And then you get this thing where you have this possibility of an accordion. See, like an accordion folds up, it's made up of fixed length Kuhn steps, and you can take the accordion and open it up or shrink it down. So in that case, and there's not much energy change in taking the accordion and pulling it. So like an accordion, you could have an accordion that has a high modulus and it would still be extensible. So you can think just the hinges, and then the thing is really stiff, but it can extend. That's the idea. I'm not saying it's right, but that's the idea that could happen. I mean, it's hard to see. He's forced it to make it right. Accordion is pretty easy to see, and you can pick up an accordion and play it, right? So, but basically, this thing's a little bit harder to see exactly because, yeah, the Kuhn length, and you should have freely jointed about the Kuhn length, so they should be able to do the corner that he has there. The idea is a freely jointed chain is the Kuhn model, so they can fold all the way back, or so they can do an accordion in theory, right? So how you accommodate that with multiple branch points coming off of it? In other words, beyond this is multiple branch points within a Kuhn length. So again, it starts to kind of look a little weird. And also you have to be a little uncomfortable with that cartoon, like that doesn't look right, just like somehow it doesn't look right. So anyway, and again, you have to keep in mind this guy's in his like he did a PhD, then he's like a couple of years maybe as a postdoc. So he's like maybe 3 or 4 years older than you, right? And so, I mean, you have to think like he hasn't been around that much, and maybe like and also he's desperate to get money, and he wants to have a thing that's going to get 1,000 citations, like what's his name's thing. So whatever. See, he's under a lot of pressure, So he did come up with this model, and if you put it out there and people prove it wrong, it's still going to have 1,000 citations. It's like the Dowd-Cotton model of the dendrimers, like it's probably wrong, but it's got maybe 2,000-3,000 citations, right? So it doesn't matter if it's wrong. They still got this paper. It's like in all the textbooks, So anyway, he's got leeway to say like it doesn't matter if it's wrong, but it's a first shot at kind of what's going on. Anyway, with his model in the scaling theory, then he can start saying, so the tensile blob here, which is a question, there's some tensile blob in like all of this, I guess. like in the other Rubinstein stuff, it's very clear where the tensile blob begins and ends for the main chain and the side chain. Here, it's like everything's kind of fluffy, right? And also like, why didn't Rubinstein come up with this Kuhn-Link thing? Kuhn-Link is in the other one too, but he didn't see any effect like that. Nonetheless, he does the same scaling arguments, and there's a lot of math to calculate, and then he can predict. The point of the scaling is he can predict these scaling regimes, and then he makes some of this, so he synthesizes it, and he does neutron scattering. Somebody tags it with deuterium, and then this peak is where kind of he's getting the distance between the things, and he's plotting out his scaling predictions, and it matches up, perfectly. So, I mean, if you call perfect, he has 1 point. So, I mean, there's 1 point that defines that scaling regime, okay, in a log scale. I mean, so you have to always these things like, I've read it somewhere. So biologists have this thing like the one hand rule or something, like cover 1 point with one hand, you still see the same thing. So here, the one hand rule, like if I put my hand over that, well, does that scaling regime exist? Well, hard to tell, In fact, like you can do that with a lot of these points. So anyway, so he proves it, and then he can also prove the mechanical. So he does this, these are experimental things that he made, and it matches up, and he can get, most importantly, the stuff he made, which he's patented. So he's got a patent on these materials too, which is a smart idea, I guess, because maybe you could make something with it. But anyway, and maybe you could use it to go to Mars, more importantly. So anyway, so he gets that behavior. That's the behavior he gets. He has 2 of them that he made. They both show that behavior. In other words, the higher the modulus, and it's elongating more and more, so potentially you could get infinite modulus and infinite elongation, which would be like I don't know what you'd use it for, like a super bungee cord, something like that, who knows what, but so anyway, so that's good. That's kind of the, I'm not sure, you could read this paper and get more and more out of it. It's good to read these things critically, but this is so thick that it's difficult to do that. And I think his math is all right. The issue to critique, his scaling math is pretty simple and kind of all right. The issue to critique is that cartoon. Like, is that possible? Is that really like possible? But I don't ask you to do that. I just say like, just what I did, describe the 2 models, and then where is the tensile blob involved in this thing? And then this is like, I guess, asks you to critique, like just say, is this believable? I mean, the experimental evidence has to be true, and he's got a patent on it, so it must be true. And then, but nonetheless, you don't have to believe his cartoon. So maybe you want to, I mean, you can say, yeah, the guy's a genius, like absolutely a genius, and like he should get the Mars grant, definitely, and like, but, or you could say, you could figure out how you think that, like, the idea of that accordion thing is insane. Because the thing, you have an accordion and each thing has 5 arms sticking off of it. How exactly does that work? Like, think of an accordion and you've sewn all the crumple things together. Like, does that really can you still play that instrument? It's like, I don't know. Anyway, so you can, if you like it, you can just say the guy's great too. So that's the homework anyway.
Professor,
Yeah,
can you change the due date to Wednesday?
yeah, if you want, yeah.
Yeah.
The due date's due on Wednesday on this already.
On Canvas, it still is today.
Oh, yeah, no, I just haven't changed that yet. Yeah, anyway, any of the homeworks you can kind of turn in late, like, because I'm still behind like 2 homework grades, so.
Okay.
Anyway, even after that, you can turn it in late if you want, but I don't recommend it because it's like not really worth it. But,
Yeah,
so,
you have to do it anyways.
yeah, so, but I'll fix on mine.
Have a good day.
Here's one.
Oh. Did I ever record it? I don't think so.